I already feel the summer has arrived here in UK.
What?
I already feel summer has arrived here because it's like 30 degrees today. So
Good for you.
well, not good. I don't enjoy it at all.
Come on, you plan to travel to Spain in summer, so you should be adapted. And actually, I forgot, where is this conference to which you go? It's in Valencia or?
No, it's in Bilbao.
Ah, in Bilbao. Oh.
Bilbao, oh, great. Very nice place. Yes.
Yeah.
Very nice place.
A bit over expensive, but okay.
Hello,
Like
Astrid.
it's a group,
Everyone.
cosmological group.
Hi, Luca.
Get
Oh, hi.
that name.
Hi, look.
Hey, Alex. Hello, Irina. Hi, Ravan. Sorry,
Hi.
I'm a bit late.
No, Irina, there is a conference called Portuguese and Spanish Relativity Meeting.
Oh, I see. I see. We maybe with Alexei we participate in such meeting maybe 10 years ago, something like this. Maybe a little bit more.
I would say even 15.
15. 15.
Again, organized by Mariam, by the way.
Okay.
Luca, are you in Italy now?
Yeah, I'm still in Italy.
He is always in Italy.
I'm leaving on Sunday.
I'm jealous. You have good pizza there.
I mean, you can get good pizza in many places, even outside Italy.
Not in
Yes.
No,
And
not
actually,
in
there is one brilliant place here in Shanghai with brilliant pizza.
Yeah, good.
Yeah. Held by Italian guy, by the way. Andrea Dazzi, who is now in Chengdu, apparently. But he and his wife are holding pizzeria in Shanghai.
Ah, they hold a pizzeria. Oh,
Yes, exactly. They established pizzeria and we celebrated there something. They make brilliant pizza, really.
interesting.
Yeah.
Oh, Branka is up here. Hello, Branka. Oh, hello.
Hello, nice to see you.
Nice to see you too.
Здравствуй, Бранко.
Здравствуй, Ричард.
Здравствуйте, Бранко. Рад вас видеть. Все нормально у вас?
Здравствуйте, Владимир.
We can wait a few more minutes, right?
Yes, I think
Come.
yes.
Yeah.
Now it's left 1 minute, but maybe we can wait a little bit more.
Astrid, I don't know if you were already asked, but is it okay if people ask questions during your talk?
Yeah,
Or do you
yeah,
prefer?
absolutely. Yeah.
Okay. Perfect.
How many people? 20.
It's
Okay.
increasing.
Okay, maybe 1 minute more.
Mhm.
Can wait. I'm a co-host now. Okay, good. Okay. Astrid, maybe you can show your transparencies just now so I can read your title. Okay, thank you. Okay, I think we have to start now. Hello, everybody. Today we have a pleasure to have a talk by Astrid Eichhorn. She will tell us about quantum gravity and its connection to observations. Please, 1 hour.
Thanks. Thank you very much for the invitation. It's a pleasure to speak in this seminar. And I should say I'm happy to be interrupted with questions at any time during the talk. So I'll be talking about my personal perspective on how to connect quantum gravity to observations. And let me start by making a more general comment that the link between theory development on the one side and experiment and observation on the other side that really underlies all of natural sciences, that is an absolutely necessary link in physics. And the fact that this link might be difficult to establish in some research fields does not mean that we are allowed to give up on trying to establish it and just proceed purely on the theoretical side. But of course, in quantum gravity, that is maybe to some extent what is happening in the field a little bit. So in quantum gravity, the connection between theory and observations is notoriously hard to establish. And this, I think, is one of the reasons why we have a number of different approaches to quantum gravity, and we do not really understand the relation of these approaches to each other. So we don't really understand whether they are just mathematically distinct way of encoding the same physics, because we don't understand their physics implications that well. And also, we don't know whether any of these approaches is actually on the correct track to describe quantum space-time in our universe, because of this lack of a connection to experiment and observations. Now, why is it that it is so challenging to test quantum gravity? Well, you'll of course tell me, well, that is because quantum gravity lives at the Planck scale, and expressed at the length scale that is just much smaller than length scales that we have direct access to. Similarly, expressed as an energy scale that is a much higher energy than we can reach in experiments. And so if this is true, then indeed it can become quite challenging to test quantum gravity. However, it actually makes sense to question this a little bit, because where we get the Planck scale from is really a somewhat simple or naive dimensional estimate, where basically what we do is we take 3 constants of nature, h bar for quantum effects, 1/c for relativistic effects, and Gn, the Newton coupling for gravitational effects, and we combine them into a quantity of units of length or energy. And then this is what we expect characterizes quantum gravity. However, in doing so, in constructing this Bronstein cube, where gravity is sitting on this elusive corner back here, in doing so, we actually haven't used any information, any dynamical information on the actual theory of gravity whatsoever. So note that we can construct these scales without knowing anything about that theory. So it's a very simple estimate based on what we know about the other theories of nature, based on what we know about these limiting cases. So this lacks any information on the actual dynamics of quantum gravity. Also, it assumes naturalness, meaning that once we have constructed this length scale, we assume that we are not allowed to put a very large or a very small number in front of that. And naturalness, of course, has been a guiding principle in fundamental physics for quite a while. However, we now have at least 3 examples where naturalness fails. One is the cosmological constant that is observed to be much, much smaller than its natural value at the Planck scale. The other is the Higgs mass or Higgs vacuum expectation value, that is also observed to be many orders of magnitude below its natural value. And the last is the strong CP problem, so the neutron electric dipole moment linked to the QCD theta parameter that is much smaller than 1 and seems to be quite close to 0. And so we have these 3 examples that highlight that maybe nature is not that natural after all. And what that would mean is that once we have made such a simple dimensional estimate, we are actually allowed to put a very large or a very small number in front of that. And that, of course, tells us that we don't really know that the scale where we expect quantum gravity effects to set in so well. And then the last issue with this estimate of the quantum gravity scale is that it makes the assumption that quantum gravity comes with just a single scale, and that you cannot have settings where, for instance, some effects of quantum gravity manifest themselves at one scale and further effects of quantum gravity kick in at another scale. But there are actually quantum gravity models out there which do come with several distinct scales, which can be even quite separated from each other. And so based on all of that, I think it makes sense to challenge this assumption that quantum gravity kicks in at the Planck scale, and therefore approaches to test quantum gravity observationally, I think should come in 2 ways. First of all, we should be agnostic and not make the assumption that quantum gravity effects come in at the Planck scale, but just think about some new physics scale in gravity and ask the question, how much can we constrain that new physics scale from observations? And then the second part of the strategy is to say, well, maybe indeed the simple or naive dimensional estimate is quite correct, and the effects of quantum gravity are in fact contained at this very tiny or very, very high energy scale. Are there then any lever arms that we have at our disposal that could enhance tiny effects to make them accessible in our observations? And in this talk, I'll talk about both aspects of this strategy. I'll be doing that in 2 testing grounds for new physics and gravity. The first testing ground is black holes, or more precisely, black hole shadows. So there are several approaches to black hole shadows beyond general relativity. The first is a parametrized approach. So here one just considers very theory agnostically all possible deviations of the spacetime metric from the Kerr spacetime, and then one tries to understand how these deviations from Kerr can be constrained observationally. The advantage of that approach is that it's really comprehensive. If you cover all possible deviation parameters here, then you're covering all possible metrics that could come out as solutions of all possible theories, as long as gravity is still described by a metric. However, these deviation parameters, they don't have any connection to a fundamental theory any longer. So even if you were to see in observations that a spacetime metric which has a certain deviation parameter from Kerr seems to be observationally favored, it's not very clear what that would actually tell you about the fundamental theory. So then you can take sort of the opposite approach. I'll call it a principled approach, where you really start from a given theory beyond GR, and then you construct spinning black hole solutions, and then you calculate black hole shadows in that theory within a realistic setting in terms of accretion disk and all of that. So that's actually quite a extensive program that you would have to do in each single theory beyond GR. And of course, doing that then in many, many theories becomes really overwhelming. And that approach might actually be doing a little bit too much, in the sense that the observations that we have access to from the Event Horizon Telescope and its next generation counterparts, those observations have finite resolution and a number of other limitations. And so they can't actually probe all of the details of black hole shadows in theories beyond GR. And so we actually don't need to know all of that detailed information. And so together with Aaron Held, I've developed an approach that tries to combine the best of both worlds. We've called it the principled parameterized approach, where we calculate the black hole shadow in models for black hole spacetimes that we base on general principles. So on the one hand, we take parts of the principled approach in putting general principles into the construction. On the other hand, we try to still be fairly general because we parameterize families of metrics obeying those principles. And I'll tell you a little bit about how that works and what type of metrics you can in this way motivate, and then what we can say about these metrics from actual shadow observations. So the three principles that I focus on are regularity, which means absence of curvature singularities, locality, which you can think of as being motivated from an effective field theory type perspective, and the last one is simplicity, and I'll talk more about what that actually means. So what one does in this type of approach is one starts from a general line element. And just to be pedagogical in this presentation, I'll focus on this spherically symmetric case. You can do the same type of thing in the axisymmetric case, so I refer you to the literature for that. Expressions just become much more lengthy if you have spinning metrics. So in the spherically symmetric case, there's the Schwarzschild solution where this function f takes this form here. And now we implement the first principle, namely regularity. So we upgrade that to a non-singular spacetime. And we do that by including a sort of correction factor that captures the effects of new physics beyond GR. And now the second thing that we demand is a locality principle. And what we mean by that is that the upgrade that we do only depends on the local curvature scale. So you can think of that as being motivated by effective field theory, where you would have higher order curvature terms beyond GR. And at a point in a spacetime where curvature invariants become large and exceed certain critical values, these higher order corrections beyond GR would kick in and make the metric deviate from its GR counterpart. And that's the idea behind this locality principle. So this means that this correction factor here is a function of the local curvature scale, for instance, the Kretschmann scalar. And then for dimensional reasons, it comes with a new physics scale. And this is the quantity that we ultimately want to constrain. Now we demand regularity. And that tells us that at high values of the curvature, the leading order term here has to be 1 over square root of the Kretschmann scalar. And then there are even higher order corrections. So that is sufficient to remove the curvature singularity. And now the last principle that we put in is simplicity. Simplicity says that the only new physics scale that we want to introduce is the scale L new physics here. And that actually means that this correction factor has to interpolate monotonically between the behavior that we get at large values of the curvature, so where 1 over the curvature scale goes to 0, so this would be in the core of the black hole. And then far away from the core of the black hole, asymptotically, we want this correction factor to just go towards 1, so that far away we just recover the classical metric from GR. And now simplicity says that this function just interpolates between these two limits monotonically, and there shouldn't in particular be any local extrema in between, because these local extrema would define new scales. And so then this gives rise to a family of metrics that are actually quite well known in the literature. Those are regular black holes, for instance, the Dibnikova-Hayward or Simpson-Visser proposal, all of which have previously been proposed independently, but they fall into a family of metrics that satisfies these general principles. We can also ask whether this approach actually covers any actual quantum gravity theories, or whether it's just a sort of more ad hoc modification of black hole metrics. And the answer is yes, there is at least one example of a quantum gravity theory that is covered, and that is asymptotically safe quantum gravity. In that case, where this correction factor comes from is from the scale dependence of the Newton coupling. So in asymptotic safety, the Newton coupling, the classical Newton coupling, which is constant all the way to the Planck scale, becomes weakened by quantum fluctuations in the UV, where it starts to scale according to its mass dimension. So it falls off as 1 over scale squared. The dimensionless counterpart of the Newton coupling that you get by just multiplying with its energy scale squared, that is what becomes constant in the regime beyond the Planck scale. And this is probably the version of asymptotic safety that most of you will have heard about, saying that there is scale symmetry in that dimensionless couplings become constant. But what that means for the dimension full Newton coupling is that it actually falls off as 1 over the energy scale squared, which actually means that asymptotic safety corresponds to a form of weakening of the gravitational force. And so this scale dependence of the Newton coupling, that can now be included into the line element for a black hole to get a sort of asymptotic safety inspired black hole metric. In that case, we have this function here for the Newton coupling and this energy scale squared. For the case of a black hole, it again makes sense to identify that with a curvature scale, just because that's the actually only measure of energy scale that exists in a black hole. And just for dimensional reasons, we have to take the square root. And then from this functional form of the Newton coupling, we get this particular correction factor. And that is actually within the class that I talked about previously. So this does exactly that. It interpolates between a vanishing factor at 0, so that resolves the classical curvature singularity, and then it interpolates all the way to 1, so it recovers classical black holes at large distances. All right, so this principled parameterized approach to black hole metrics therefore includes at least one example of a quantum gravity theory. And so now what we can ask is, what can we actually say about observational consequences and existing constraints? And now what happens if you have this correction factor is you're essentially weakening gravity everywhere except very far out, because you can see that you're multiplying the product of Newton coupling times mass, you're multiplying that with a factor smaller than 1, and that actually means you're just weakening the effect that this mass has on the rest of the space-time. Or another way to think about it is you're weakening the Newton coupling. And what that means is that the event horizon is more compact, and it also means that the photon sphere is more compact. And the photon sphere, that is the sphere that is formed by a sort of marginally stable null geodesics. And that is what is in turn determining the black hole shadow. And so with this correction factor present, the black hole shadow is more compact. And then you can ask, how much more compact the shadow at a given black hole mass is as a function of this new physics scale. So RNP is what I previously called LNP on the previous slide. So that's our new physics scale. So what you see here in this plot is in blue, the event horizon telescope constraints on the shadow size of M87. And the continuous line is the 1 sigma contour and the dashed line is the 2 sigma contour. And then I'm showing 2 examples for particular choices of F in this family of metrics, as sort of the Hayward type or asymptotic safety inspired case, and then the Simpson-Visser case. And you can see in both cases, the larger you make the new physics scale, the more compact the shadow becomes. And you can see that in the Simpson-Visser case here, it actually leaves this 2 sigma region from the EHT observations. And so you would say that at not very high significance, but at 2 sigma significance, you would actually rule out these values of the new physics scale for the Simpson-Visser case. So what you can see from that is what you're ruling out from direct observations in this case is new physics scales, which are really close to the actual gravitational radius or mass of that black hole. So these are scales that are quite far removed from the Planck scale. I'll get to the Planck scale case in just a second. Let me first of all say that there is a second observational consequence of having this correction factor around, namely that if you go beyond the critical value of the new physics scale, the event horizon of those black holes is resolved, and so then the image changes quite significantly. So these black hole images are characterized, if you zoom in closely in simulations, they are characterized by so-called photon rings, which means that at the boundary of the shadow, you actually have exponentially closed intensity peaks. They are not resolved directly by the EHT observations because of the finite resolution. Now, if you just look at a cross-section of that image along this arrow here, what that would look like for a black hole is that essentially you have no intensity in the center, so you see the shadow, and then you see the photon rings, and then you see the direct emission from the disk. And now, if you go with L beyond this critical value, you resolve the horizon. And that means you suddenly get intensity also in the inner region of the shadow. You get these inner photon rings, which is because there is still strong gravitational lensing. But because the horizon is no longer there, these null geodesics that would usually just be, and that would usually just end up behind the horizon, they can now make it to an observer. And I'll be talking about whether or not these things can be seen with the EHT in just a second. Before that, I will discuss this question of what actually happens if the new physics scale is actually equal to the Planck scale. So we saw on the previous slide that based on the shadow size, we can only constrain new physics scales much larger than the Planck scale. So in the case that the new physics scale is the Planck scale, we need a lever arm that can enhance quantum gravity effects in order to actually make them accessible in observations. And the appropriate lever arm for a black hole is actually the spin. And this is because the following happens. If you look at what happens to the event horizon of a black hole, as you increase the spin, the event horizon becomes more and more and more compact, and there is an inner horizon, and at a critical value of the spin, which is A equal 1 in GR, the two merge, and in GR, you can't go beyond because you would leave behind a naked singularity, and so that's excluded if you believe the cosmic censorship hypothesis. You can see this in this metric element here. The two horizons are encoded in the zeros that has. At vanishing spin, which is this line here, you only have one horizon, but then at finite spin, you get the inner horizon and the two approach each other, and then you end up with this critical case in GR. Now, if you add to a near critical black hole, so a spin that is just slightly below 1, if you add the quantum gravity effect, that actually lifts this function up. And so in that case, you can then resolve the singularity and the horizon. And you can do that with just a tiny quantum gravity effect confined to the Planck scale, because spin gets you to nearly this point where the horizon is resolved. There's a caveat to that, which is that it's currently unclear whether astrophysical black holes in dynamics beyond GR may or may not actually achieve these spins close to 1 that are necessary for this mechanism to kick in. If we believe that that can happen, then what would happen at that point is that you go from a black hole, which has a shadow that really has a dark central region, you go to a case where we call that the black hole shadow lights up, because we get these photon rings inside the image, because the event horizon disappears and null geodesics can now come out from inside the black hole. And so this is similar to the case that I was just showing you in the non-spinning spacetime. And now, of course, the critical question becomes, can the Event Horizon Telescope or its next generation future upgrade, can that actually distinguish black holes from these horizonless spacetimes? And so we took our simulated images here and we put them through a simulated observation that reconstructs how the actual Event Horizon Telescope array would see images like that based on the sparse coverage that the Event Horizon Telescope has, and also based on a number of other limiting factors, for instance, the noise in the instruments. And you actually can see that both of these produce just this donut-like shape that we're all very familiar with, and do not result in images that look very different from each other. And you can make these statements more precise by actually analyzing these images in the Fourier plane, as is more appropriate for the type of radio VLBI observations. You can then ask whether the next generation Event Horizon Telescope can do better. And the next generation Event Horizon Telescope will have more resolution. And you can see that clearly in the difference between this simulated observation and this simulated observation. Here you can see that these photon rings are actually reconstructed to be much more thin as they are in the actual simulated image. And the other, for this point, critical quantity of the NGEHT is that it has a higher dynamic range. That is basically related to the sensitivity that the array overall has. And it means that there is a larger difference between the darkest and the brightest pixel in an image. So you can define this quantity here that just compares the darkest region of the image to the mean flux in that ring. And if you're really looking at a black hole, then as you increase the dynamic range or the sensitivity of your instrument, you expect that that quantity just goes down further and further and further, because you see better and better that it's really dark, that you really have a black hole shadow here. So this is exactly what you see for this case here. So this is subcritical spin. So this is a black hole. And you see that as we go to improved configurations of the array, this quantity continues to drop. And now that is actually different for the horizonless spacetime, where the MGHT can still not really resolve these inner rings, at least in the study that we did here. But there is additional intensity in the center. You can sort of see that by eye. It's just darker here than it is here in the center of the image. But you can also clearly see that in these numbers, as the dynamic range of the instrument increases, this number does not drop. And so the next generation Event Horizon Telescope will be able to distinguish those cases. And that is interesting because I told you that we get such a horizonless spacetime by going to near critical spin and then adding a quantum gravity effect that is really confined to the Planck scale. And that has a very significant difference for the simulated images, and the next generation Event Horizon Telescope will be able to probe those differences. And so that means that we may potentially even test quantum gravity with the next generation EHT. All right, so that actually concludes the first part of my talk, why I wanted to talk about black holes as a testing ground for quantum gravity. I'll now switch to a second testing ground, namely particle physics. And before I do that, I'll just stop very briefly to see whether anybody has questions on the black hole part right now.
So questions, please. Who would like to ask something? Please raise the hand or just asking.
And if there are no questions right now, then obviously I'm also happy to talk about the black hole part after I've wrapped up the full talk.
Okay.
All right. So there doesn't seem to be any urgent question right now. So then let me continue with the second testing ground, which is particle physics. So here I'll focus only on that case where the new physics scale is actually the Planck scale. And again, as in the case of the black holes, we need some form of lever arm that will translate effects at the Planck scale to observable scales. And in the case of particle physics, that lever arm will be logarithmically running couplings. So in order to explain that in a bit more detail, I'll actually use an analogy. And with that analogy, I'll challenge the expectation that we usually have that says that in particle physics at LHC scales, we can no longer infer any information on quantum gravity scales. So the analogy that I have for that is a different model. Namely, imagine that we are not interested in quantum gravity at the Planck scale, but we're interested in microscopic models of different molecules at molecular scales. And then as we zoom out to larger and larger scales, a lot of that microscopic information gets lost. And at macroscopic scales, we end up with a hydrodynamic description for many of these systems. And so we end up with something that isn't so very different for these different microscopic scales. And so in the analogy, LHC scales would be these macroscopic scales, and these would be the only scales that we have observational access to. And so this is exactly the picture that we usually have in mind, starting from different assumptions about what Planck scale physics is. Although, let me just briefly advertise that potentially asymptotic safety and string theory are more closely related than we typically think. But even if we assume that they are different, the picture that we usually have in mind is that as we zoom out to LHC scales, the microscopic information gets lost. We just get to the standard model in both cases, and we can therefore no longer infer anything about which of these underlying models was actually the correct one. And that expectation is not completely correct. And you can see that by going back to the analogy, because while it's true that most of the microscopic information gets lost, is not all of it. And there are imprints of microphysics at these macroscopic scales. And a good example for that is the viscosity. So the viscosity arises directly at the microscopic scale from the interactions of the different molecules. But the viscosity is also something that you can measure at macroscopic scales, basically at everyday scales of sort of centimeters and meters. And so it's an observable in the macroscopic regime that is directly determined by the microphysics. And if you can calculate the viscosity in these different microscopic models, then a measurement at much larger scales will allow you to infer which of these microscopic models was correct. And so to translate the analogy into particle physics, we now need to identify which couplings in and beyond the standard model are sensitive to the microphysics in this way. And in particle physics, we have two types of couplings at our disposal. We have the so-called higher order couplings, for instance, something like a Higgs to the 6 interaction here. And those couplings are those that satisfy this sort of standard expectation, namely they satisfy universality, which means that even if you choose their values at the Planck scale to be quite different, you're very quickly drawn towards one universal curve, and at low energies, you can no longer distinguish what the microscopic value was. However, in the standard model and beyond, we also have logarithmically running couplings. And for a logarithmically running coupling, the initial value at the Planck scale, a memory of that is actually preserved all the way down to the electroweak scale. So you can see that differences of order 1 at the Planck scale do translate into differences of order 1 at the electroweak scale. And so the idea here overall is then the following. If quantum gravity can fix the Planck scale values of some of the couplings in the standard model, and here I'm showing you the 3-gauge couplings of the standard model and the largest 2 Yukawa couplings and the Higgs quartic coupling. So if quantum gravity can fix the Planck scale values of these couplings, then you can calculate the low energy value just from the standard renormalization group flow. And because there is a logarithmic dependence, a change of order 1 here at the Planck scale manifests itself in a change of order 1 at low energy scales. And that actually means that whatever we predict here at the Planck scale can actually be tested using data from the LHC. There's also a sort of a benefit for particle physics from this scenario, namely that the couplings in the standard model, they're all free parameters. So while we can calculate their renormalization group flow, if we have an initial condition, we cannot calculate that initial condition. So each coupling comes with one free parameter, which needs one measurement to determine its value at one scale. And now if quantum gravity indeed predicts the Planck scale value of a coupling, that means that it also eliminates a free parameter from the standard model, and we're getting a more predictive particle physics setting. Now, the particular example that I focus on here for that is asymptotic safety that I've already talked about briefly before. So asymptotic safety says that there's quantum scale symmetry in the UV, which means that the Newton coupling is constant, its dimensionless version. And if it works for a gravity meta theory, it means that the couplings in the standard model either are constant or approach asymptotically free fixed points. And indeed, evidence in the literature suggests that this type of picture could work out. And even more interestingly, a number of the couplings in the standard model would then actually be predicted at the Planck scale by requiring quantum scale symmetry in the UV. And because this point that there are predictions arising out of quantum gravity for particle physics couplings at the Planck scale, because this point will be really crucial for the rest of the talk, I'll spend a little bit of time to explain the mechanism behind that predictive power to you. So the predictive power arises from the fact that quantum fluctuations can either screen or anti-screen interactions. And we know both of these from the standard model. So for instance, in QED, we have screening effect of quantum fluctuations, which means that the beta function starts with a positive term. And that means that the value of the coupling decreases as we lower k. K is an RG scale or a momentum scale. And so as we go towards lower energies or larger length scales, the coupling decreases, so it's screened. In QCD, we have exactly the opposite behavior. We have a negative sign here that gives us anti-screening, and that means that the coupling increases as we go towards larger scales. And now, if we want to achieve asymptotic safety, we basically have to balance screening with anti-screening contributions. And in this way, we can get a non-trivial zero of the beta function. And you see a simple example here. So this alpha star, that is the asymptotically safe fixed point value, at this value, the screening and anti-screening contributions balance out and we get scale symmetry. In this particular toy model here, I've chosen the leading order term to be the screening term and the higher order term to be the anti-screening term. And that actually means that if you deviate from the scale invariant fixed point value to slightly lower values of the coupling, the screening effect kicks in and drives the coupling towards even lower values. If you deviate to slightly larger values, then the anti-screening effect kicks in and drives you towards even larger values. And that actually means that even if you start with scale symmetry in the far UV, at the Planck scale, you can reach a whole range of values for the coupling. And so that means you cannot make a prediction. The opposite is true for the so-called irrelevant couplings. So here, the leading order term is an anti-screening one, and the higher order term is a screening one. And this actually means that quantum fluctuations, no matter whether you're at larger or at smaller values of the coupling, quantum fluctuations always drive you back towards scale symmetry. And so if you start with scale symmetry in the far UV, you necessarily end up with one particular value of the coupling at the Planck scale. And so this is how you achieve a prediction of the value of the coupling from asymptotic safety. And so this brings me back to this slide that I showed previously. This indeed seems to be the case for a number of couplings in the standard model, that they fall into this scenario of being irrelevant couplings, where quantum gravity fluctuations generates anti-screening contributions and generates a prediction for the value of the coupling. And I will give a proof of principle by talking about Yukawa couplings. And specifically, let me focus on the top Yukawa coupling here. So the one loop term in that beta function is a screening one. And then the quantum gravity contribution can be calculated to kick in at lower order. So this actually gives you the leading order term and an expansion in the coupling. This Fy encodes the effect of metric fluctuations, and it depends on the gravitational couplings. I'll talk more about the depends in a second. For now, it's only important to know that this Fy is constant above the Planck scale, where there is scale symmetry, and the gravitational couplings are constant. And then it drops to 0 below the Planck scale. This is because quantum gravity fluctuations decouple below the Planck scale. Now, the sign of Fy actually depends on the values of the gravitational couplings at high scales. And that is actually really interesting for the phenomenology. So let's take a look at both scenarios, both signs, to see what the phenomenological consequences are. So if Fy is negative, then we have a screening and another screening term. And that means that we have only an infrared attractive free fixed point, which means that the only way to get a UV complete model is to set the Yukawa coupling to 0, where it will then remain. And so therefore, Fy smaller than 0 gives us a prediction that the top Yukawa coupling vanishes in the infrared. And we can compare that to actual LHC data, which has, with, I believe, 5 sigma significance, established the top quark Yukawa coupling to be non-zero. So if Fy were smaller than 0 in asymptotic safety would be in trouble regarding this observation. Now, if we have the other scenario, if Fy is larger than 0, then we have a screening competing with an anti-screening term. And that actually means that we can get asymptotic safety at a particular value of the coupling. And it also means that we get a prediction from scale symmetry here. Furthermore, if the value of the Yukawa coupling is low enough at the Planck scale, then the gravity contribution dominates and generates asymptotic freedom. And so this means that this unique value that comes out as an asymptotically safe prediction, that also serves as an upper bound on viable values of the coupling, because lower values of the coupling at the Planck scale correspond to asymptotic freedom. Higher values, in contrast, they run into a Landau pole. And so what you get from this setting is a prediction that at the same time acts as an upper bound on the value of the Yukawa coupling. You could have an asymptotic safety. Now, given these two different possibilities, of course, the crucial question actually becomes, what is the value of Fy in asymptotically safe gravity? And it depends on the gravitational couplings. So this is the Newton coupling and the cosmological constant that are mentioned as counterparts actually in the microscopic regime. And in this regime here, Fy is smaller than 0, and this is the regime Fy larger than 0, which would be compatible with phenomenology. And now something interesting happens, because if you look at where the fixed point lies with one generation of matter, in this work here, we found a fixed point value that is in this regime where you cannot get a non-zero fixed point value for the top. And then as we add a second generation, we are still in the not viable regime, but with the third generation, we actually end up in the viable regime. It has to be said, though, that this retrodiction, or the value of this fixed point here, that is subject to significant systematic uncertainty. So currently we can't know for sure what the actual asymptotically safe prediction for the top quark-Yukawa coupling is. Now, because we have these systematic uncertainties, this motivated us to develop an approach that I'll also call the principled parameterized approach to asymptotically safe gravity matter systems. The starting point here is what I just told you previously, that the gravitational contributions to the scale dependence of matter couplings, they are not known quantitatively precisely because there are systematic uncertainties in these calculations. However, we do know their qualitative form. So we know that the effects are linear in the standard model couplings, which is basically because gravity couples to the stress energy tensor of a matter theory. We also know that the effects are only present beyond the Planck scale because gravity actually turns off dynamically, or quantum gravity fluctuations become negligible below the Planck scale. And third, we know that the effects are the same for all different gauge groups or for all different flavors, because gravity is blind to internal symmetries or internal charges. It is only sensitive to the space-time properties of a field. And so based on these three properties, we can actually parameterize the gravitational contribution to the beta functions of the gauge couplings in the standard model, and also to the Yukawa couplings. And here I'm showing you an example where I'm focusing on the third generation of the standard model. So I have three gauge couplings here, but just one parameter Fg that comes from quantum gravity because of this blindness to internal symmetries. And then I'll have two Yukawa couplings, top and bottom, but just one parameter Fy. And so we have this two-parameter plane, Fy and Fg, and then we can ask, what are the predictions that come out of here? And actually the top Yukawa coupling, bottom Yukawa coupling, and abelian hypercharge, they're all irrelevant couplings, so they're all predicted at the Planck scale. And so quite surprisingly to us, these predictions actually fall into the vicinity of the experimentally measured values. These bands here, they are sort of 10% bands around the actual experimental value. And you see that these three bands intersect here at a location where you get something that is very much like the standard model at lower energies. And now the same principled parameterized approach has then been used more broadly to explore physics in and beyond the standard model with quantum gravity. And for the remaining time, what I would like to highlight is how we can take these type of ideas beyond the standard model to think about the dark universe. So we know that the standard model that we've just talked about actually only makes up 5% of the energy density of the universe. The remainder is dark matter and dark energy. And what these sectors have in common is that we have many, many phenomenological models in both of those. So to explain dark energy, we have a cosmological constant, and then many, many different models of dark energy. To explain dark matter, we have primordial black holes, potentially modified gravity, and then many, many, many models of new particles. And so the idea here would be that maybe only some of these explanations, or maybe even none, are actually compatible with asymptotically safe quantum gravity. So if you buy into asymptotic safety as a new theoretical guiding principle, that could actually narrow down these choices that we have in the dark sector quite significantly. So just as one example, let me highlight recent work together with one of my PhD students, Rafael Lino dos Santos, and Fabian Wagner, who was then a visiting PhD student in my group and who's now a postdoc in Salerno. So together we looked at a particular model of dark energy, namely a Horndeski theory, and we focused on the very simplest Horndeski theory that is so far compatible with observational constraints. And we found that asymptotic safety predicts the couplings of that theory to vanish. in particular that coupling that you would actually need for that to become a viable dark energy model. And so that means that asymptotic safety actually is not compatible with the simple Hondesky model as a theory of dark energy. So that's one example for the predictive power, where you take one of these many phenomenological models and you find it's actually not compatible with asymptotic safety. And the further examples that I go into now are actually different dark matter models. So one of the key challenges, I would say, with dark matter is that we have a huge parameter space spanned by the scattering cross-section and the mass. And this parameter space is filled with different theoretical proposals, some of which you see here. And then, of course, experiments try to probe as much of that parameter space as possible. But just from a theory point of view, actually, these are just way too many choices. And it would be nice to have a theoretical guiding principle that tells us, well, this particular model of dark matter is somehow preferred. And so what I'll explore is whether asymptotic safety could become such a guiding principle. So this story then starts with sort of the vanilla model of dark matter, namely just a singlet dark scalar, phi, that is coupled to the Higgs of the standard model through a portal coupling. Through the portal coupling, it's produced in the early universe, and through that portal coupling, you can also search for that dark matter scalar, for instance, through LHC or through xenon. Now, if you calculate the quantum gravity effect on that Higgs portal coupling, that's also encoded in one of those parameters from asymptotically safe quantum gravity that turns out to be larger than 0. So this is something that is known quite robustly. And that actually means that quantum gravity fluctuations drive that portal coupling to 0 at the Planck scale. And once the portal coupling is 0 at the Planck scale, in the simple model, it's not regenerated. It remains 0 at all scales. And so therefore, a single dark scalar decouples in asymptotic safety, and it cannot be thermally produced in the early universe. And so the simple vanilla model of dark matter does not work. You can then ask, oh, and by the way, this is nicely compatible with the searches for the Higgs portal model, which have just narrowed down the parameter space more and more, but not yet seen anything. But then, of course, one of the things that you can ask is, could you regenerate the portal by adding more fields in the dark sector? And there are two examples of that. So Manuel Reichert and Yuri Smirnov have looked at a setting with a dark gauge group with kinetic mixing that is actually able to regenerate the portal at low energies. And together with a former PhD student, Martin Pauli, I've looked at a dark Yukawa coupling to a dark fermion, which would regenerate that portal. And I don't want to go into details on these models. I would just like to present one key message about them, which is that these are strongly constrained settings within asymptotic safety. For instance, the second model here, if you look at it as an effective field theory, it has 6 free parameters, which are the scalar mass, the quartic coupling, the Higgs portal coupling, the mixing angle, the Yukawa coupling, and the non-minimal coupling. And if you want to make the model asymptotically safe under the impact of quantum gravity, you can do that, but you can no longer choose the values of these couplings freely. There's just a single free parameter that remains. And so then you can make these type of plots where in this 6-dimensional parameter space, there's only one line that you can reach at low energies, starting from an asymptotically safe regime. And so the key message from that is that asymptotic safety really has predictive power for the dark sector and strongly constrains such settings. So to sum up on what we know on the Higgs portal to dark matter, the vanilla model is ruled out, which I think is a good thing that establishes the predictive power. You can then build extended dark sectors where there's also predictive power. They have reduced parameter spaces, but just from the point of view of whether they are convincing as dark matter models, they lose a little bit because we have added new degrees of freedom here only to circumvent this result that you actually set the portal to 0. And so from that point of view, these, I would say, are not very convincing models of dark matter because you only need an extended dark sector to come around to get around this sort of no-go result from asymptotic safety. And so therefore, we turned to another model of dark matter, which is simpler, and that's axion-like particles. So an axion-like particle is a pseudoscalar that can couple to this combination of field strength times dual field strength in electromagnetism through the axion photon or the Alp photon coupling. It is actually an ultralight dark matter candidate. And the way to search for it is by doing light shining through walls experiments, where this term actually allows you to convert a photon into an Alp in a strong magnetic field. And then the Alp, because it's very weakly coupled to matter, traverses a wall. And in a second magnetic field, it can be reconverted into a photon. So effectively, you've shown light through a wall. So now what I recently looked into together with one of my postdocs, Gustavo de Brito, and also with Rafael, who was involved in one of the previous projects, we looked at the effect of asymptotic safety on this Alp coupling. And there's a gravitational contribution to the beta function of that Alp coupling. And you can see from that beta function, because these other two terms are positive, that the only way in which you can get a non-zero fixed point would be if this contribution from gravity, this FGA, would be larger than 2. Now, if the gravity contribution is larger than 2, you can already see that that somehow corresponds to strongly coupled quantum gravity, because the other loop corrections you can see are these numerically smaller factors. And indeed, if you look at the gravitational parameter space spanned by the gravitational coupling and the cosmological constant, this hatched region here, excuse me, this hatched region here is where Fg would be larger than 2. And you see it lies at quite large values, microscopic values of the gravitational coupling. And indeed, our best guess for the fixed point value under the impact of standard model matter lies somewhere here, much closer to not so strongly coupled gravity. And so from that result, we drew the conclusion that there are no Alps in the asymptotically safe landscape, which is also interesting because Alps actually very generically occur in string theoretic settings. So string theory apparently naturally gives rise to axion-like particles. And here we find that that does not seem to be the case in asymptotic safety. And that actually means that searches for axion-like particles can in fact give us some information about quantum gravity. And so that brings me to my conclusion. I started my talk by emphasizing that this link between theory development and observations and experiments is really absolutely critical in all areas of physics, and that includes quantum gravity. And then, of course, the challenge is that we expect quantum gravity effects to kick in at the Planck scale. I talked about a little bit that expectation might not actually be correct. And so observationally, it makes a lot of sense to use any observations that we have to just constrain the new physics scale in gravity in a more theory agnostic way without putting in our theoretical bias that we expect it to kick in at the Planck scale. But then, of course, it also makes sense to think about how could we access quantum gravity observationally if its effects are really confined to the Planck scale. And here we need to find appropriate lever arms that make the Planck scale accessible in observations. And so I talked about black hole shadows as the first testing ground, where I told you that we can constrain large new physics scales by just looking at the size of the shadow. And if you have a new physics scale at the Planck scale, that you can then use the spin as a lever arm to enhance these effects, and you can get these horizonless spacetimes potentially. And then I talked about particle physics as the second testing ground, where the logarithmic running of couplings serves as the lever arm that translates effects at the Planck scale, where asymptotic safety makes predictions for some of the couplings, and this logarithmic running translates those into predictions at the electroweak scale. So with that, let me thank you for your attention, and I'm looking forward to questions.
Okay, thank you very much, Astrid, for your very informative talk. And I see several questions. The first question comes from Shravan. Shravan, please ask your question.
Hi, Astrid. Thanks for the very nice talk. Well, I have 3 questions.
Okay.
Okay.
Well, the first one, well, as you motivated, like black hole shadow is an interesting ground, and also the particle physics. Well, I'm curious, well, at least for quantum gravity, early universe cosmology, CMB, and gravitational waves are very good testing grounds. Do you have some comment about that in the context of asymptotic safety?
Yes, so there have been a few works that sort of looked at inflationary settings in asymptotic safety. For instance, one of the things that you can do is because asymptotic safety naturally gives you higher order curvature couplings, such as R squared, you can ask, can you actually get something like Starobinsky inflation? And of course, then the corresponding predictions that makes for the CMB. And there is work by Frank Sauersig and collaborators who've explicitly shown that indeed, because the curvature squared coupling is related to a free parameter of the setting, you can indeed find RG trajectories that connect an asymptotically safe fixed point with the value for the curvature squared coupling that you would need in Starobinsky inflation. Going beyond that, of course, one of the challenges there is in this whole area of early universe cosmology is to disentangle the effects of quantum gravity from the effects of putting in some scalar field with some dynamics.
Okay.
But in principle, you would of course expect that asymptotic safety has some predictive power, and if you do the same type of program that I talked about for dark matter, if you do that for inflationary settings, then you would presumably also be able to see that some inflationary settings are ruled out and others are compatible with asymptotic safety. And then that is, of course, something that you can then compare with the data.
Okay, that's interesting. And my second question is related. I was a bit confused in the first part and second part of the talk. So if the new scale is Planck scale, right, which is what actually assumed in the many computations of asymptotic safety, am I correct?
Yeah. So in asymptotic safety, you can lower this transition scale to the fixed point regime if you couple many matter fields. Then that can get the scale lower, but I mean, you would already need quite a few matter fields to get to something like the gut scale. And so in order to make that scale much larger, you would need, I mean, unrealistically high number of matter fields. So we expect in asymptotic safety that the scale is indeed sort of somewhere between the gut scale and 10 to the 20, 21 or so GeV.
So there is a window. So your expectation is it is somewhere between the gut scale and the Planck scale.
Yeah.
Okay. So okay, then I understand. So in the case of black hole shadows, you are kind of designing some observable if the Planck scale, if the new scale is the Planck scale or not. So am I correct?
Yes. So I mean, in the case of black holes, right, there is this one way of probing just very large new physics scales. And so that is not something that you would expect from asymptotic safety. That might be something that you could potentially see in other quantum gravity approaches or potentially just classical physics beyond GR. But if the quantum gravity effects are really at the Planck scale and they are of this type as they are in asymptotic safety, so that they lead to a resolution of the singularity, then indeed you could have a setting that high spin together with quantum gravity resolves the horizon, and then you get these horizonless spacetimes potentially. Okay,
thanks. Third question, which maybe maybe a bit of provocative question. I like the concept of asymptotic safety. It's very interesting, and it maybe the feature required for a UV completion. I'm wondering, is there any observable way which we exactly at least rule out the present formulation of asymptotic safety, or confirm, rule out or confirm? Definitely, because you showed the predictions with respect to particle physics and more with respect to particle physics, and I'm just curious if there is a way to confirm or rule out with a specific observation. It be not ruling out the concept, but maybe I do not know. Well, is this asymptotic safety can be achieved in many ways, or it's the only way the way you are studying with respect to the RG flow?
So I mean, you can in principle get asymptotic safety not just in gravity with the standard model, but also if you add a certain number of beyond standard model fields. So you do have some sort of wiggle room if, for instance, the predictions of asymptotic safety of gravity with the standard model, if those turn out to be ruled out, then you have some wiggle room where you add a certain, beyond standard model fields that shifts fixed point values a little bit, and then you could see whether those predictions match or not. The current challenge with that is that, as I said, there are systematic uncertainties associated to these calculations. And so why we have sort of these mechanisms for predictions, and we see that they give us sort of standard model-like structures, we don't have the systematic uncertainty enough under control in order to really be able to say, the top mass is predicted to be exactly 170, and that is not compatible with observations. Right? So that is just something that requires more work.
Okay.
And unfortunately, other ways of ruling out asymptotic safety in the sort of testing sort of for smoking gun features of the scenario, in contrast to these more sort of maybe indirect tests that I'm looking at. In order to really sort of look at smoking gun features of asymptotic safety, you would really have to be able to probe the scale at which the system transitions to a scale invariant regime, because then you would see scattering cross sections and things like that change quite dramatically. But I mean, that is presumably close to the Planck scale, and so nothing that we will be able to do in experiment anytime soon.
Okay. Thank you.
Okay. The next question is from Dipan Bitar. Please ask your question, Bitar.
Yes, ma'am. Am I audible?
Yeah.
Please.
Yeah. Will there be any effect of the asymptotic safety on the spontaneous symmetry breaking which happened in the early universe, and any observable effects of that?
You mean on a spontaneous symmetry breaking in the Higgs sector?
Yes.
Yeah, so in fact, there's work by Christoph Wetterich and Misha Shaposhnikov that actually predates the Higgs discovery, where they explained that one would expect asymptotic safety to give a prediction for the quartic coupling of the Higgs, and that actually translates into a prediction of the Higgs mass, and indeed a prediction that is within a few GeV of the experimentally measured value. So that would then give you something that is again very standard model-like, and so not very different from the standard electroweak phase transition. It becomes interesting if you go beyond the standard model. So there are models where you extend, for instance, the Higgs sector, or you have some dark sectors that go through phase transitions. And if these phase transitions are of first order or involve a U1 sector, they can give rise to stochastic gravitational wave backgrounds, either from the phase transition or from cosmic strings. We're just currently looking into one of those settings and find that it's quite constrained by asymptotic safety. And so if you just look at the many models beyond the standard model that give you these stochastic gravitational wave backgrounds that you can then potentially probe with pulsar timing arrays and so on, not all of these settings are compatible with asymptotic safety. And so that means that future limits or even detections of a stochastic gravitational wave background by pulsar timing arrays, that would be quite interesting in terms of whether or not that comes from models that are compatible with asymptotic safety. But we've only just started to look at the first such model, so there's more work to be done there.
And for just one more question, for the black hole shadow, if we consider a charged rotating black hole, in that case, will there be two effects? One due to the quantum gravity, and one due to the change in the QED scale because of the asymptotic safety?
I didn't fully understand. Are you asking about a charged black hole in asymptotic safety?
If we consider charged black hole, rotating black hole, and we consider this, and we consider this the same shadow kind of experiment, will there be an additional effect due to the change coupling of the QED when considering the asymptotic safety?
So for the QED coupling in asymptotic safety, there is an upper bound that we get, and that upper bound is currently about 30% above the measured value, which means that we believe that we can in fact accommodate the correct value of the QED coupling in asymptotic safety, and so that wouldn't change. But of course, if you look at a black hole that actually carries charge, which, I mean, of course, we don't believe is relevant astrophysically, but if you just look at that solution theoretically, you would, of course, still have the quantum gravity effect just to sort of resolve the singularity. So indeed, you would have overall on the shadow, you would have an effect both from the charge and from quantum gravity.
Okay, and just one last the function which you define f and p for the black hole, if we consider a singularity like a matter bounce in the loop quantum gravity, will that still stay monotonic if we consider pre-bounce cosmology and post-bounce cosmology both? And yeah, that.
I'm not immediately sure what the answer is to the question about the bounces. What I can say is that there's work, of course, on just black holes in loop quantum gravity by Ashtekar and others, and they find effective metrics which also fall into this regular black hole class, and I believe that they satisfy at least the regularity and the simplicity constraint. I'm not immediately sure whether or not they satisfy the locality principle. We've not looked at that in detail yet.
But
this F also has this type of behavior that it goes to 0 at the core of the black hole, and it approaches 1 at large distances.
But if we don't consider the black hole singularity, but we consider the early universe singularity, the naked singularity, will this monotonic structure still remain if we consider a bouncing cosmology?
Yeah, I'm not sure what the answer to that is, because I've not looked at the corresponding equations. So yeah, I can't tell you anything useful at this point.
Okay, thank you, ma'am.
Okay, next question from Hong Wu.
Yeah.
Please ask your question.
Yeah. So thanks for your next talk. I have a question. For a long time, I read, I hear that the LSD can be created, can create the black hole. What mechanism to accept this phenomena? What mechanism? So what mechanism to create a black hole in LSD scale?
Did I understand correctly? You're asking what the mechanism to create a black hole in asymptotic safety would be?
In LSD scale. In LSD scale, because for a long time, I hear that LSD can create the black hole.
I didn't understand what it is that creates the black hole.
Yeah, for a long time I hear that the LSD can create this, and I read some paper. Yeah.
I'm not sure I entirely understand the question. So let me try to answer, and then you can tell me whether I understood correctly what you wanted to know. So the creation of black holes for astrophysical black holes in asymptotic safety, that isn't modified from sort of the standard story. But of course, what an important question is whether in high energy scattering, you actually create black holes at the Planck scale, which would mean that you don't actually need something like an asymptotically safe regime. And that is true, that you create a black hole in particle physics scattering, at least we believe that is true, if you just use the standard Einstein equations all the way to the Planck scale. And of course, that is not something that we believe is correct, because we believe that higher order curvature operators become important in the vicinity of the Planck scale. And so therefore, these sort of simple arguments that tell you that, you know, once you have combined, once you have concentrated enough energy in a sort of Planck-sized region, that will create a black hole. That conclusion is a little too hasty, because it is based on using the Einstein equations. And in asymptotic safety, higher order curvature operators are important. And so therefore, we can't use this simple argument. It is, however, an open question whether if you would do high energy scattering with Planckian energies within asymptotic safety, whether or not you would actually produce black holes.
Yeah. Thank you.
Okay, let's go to the next question. Well, the next question is from Ariel Vini. Please, Ariel, ask your question. Are you here? You, please, you have no voice. We can't hear you. Okay, Ariel, we can't hear you. Okay, maybe we go to the next question, and to this question we can return a little bit. The next question from Vyacheslav Dokuchaev. Vyacheslav, please ask your question. Слава, вас не слышно. Включите звук, пожалуйста. Slava, we can hear you.
Here,
Please
I'm
switch-
here. You
now
are
it's okay.
hearing me.
Yes, please
Thank
repeat
you
your
very
question.
much for this impressive review of the problem for verification of the different gravitational theory and quantum gravity. And I see that your vision is in the direction of the philosophy Karl Popper principle for verification of falsifiability of different theories by means of experimental verifications. And my question is, what is your personal vision in view of fast technological development of experimental technique, where will be breakthrough in these fields of problems? Where will you have, suppose, some hope for the fast verification of falsifiability of some theories or some approaches? In my view, it would be in the direction of new generation of event horizon telescope. What is your vision?
Yeah, so I'm certainly also excited by the next generation Event Horizon Telescope. I think it will be able to tell us more about probing GR and finding whether it potentially breaks down. But there are, of course, other areas where technology is also fast evolving. I wouldn't be willing to bet which one of them will first give us access to quantum gravity. But of course, I'm hoping that from this type of program here, we don't only have to wait for future technology, but in particular, based on the particle physics work, that we will actually able to constrain quantum gravity with the data that we already have. So the particle physics data from the LHC specifically, so that we don't have to wait for future technologies or future observatories, but just using existing data, we can hopefully already rule some scenarios out and thereby learn more about quantum gravity.
Thank you.
Okay, more questions, please. Let's wait a little bit. Where is Ariel? He wanted to ask the questions, but I don't see him here.
Actually, I believe also there was some comment in chat.
Yes, could you please read it? Because it is too small letter.
It was a comment on the previous question. I don't know what was the previous question, but it was saying that requiring f and p going to 0 at r equals 0 implies the existence of an inner horizon. And therefore, I think loop quantum gravity black hole with bounds inside doesn't belong to that class of f and p.
Yeah, I think Chayu is actually correct with that comment. If you have a bounds, then you have a time-dependent metric, right? And so it falls outside of the class of metrics that I looked at, which are stationary metrics, both in the spinning and non-spinning case. So if you explicitly look at something like gravitational collapse and sort of bouncing matter, then that has a time dependence, and so that's a different type of sort of a different family of metrics. With one of my PhD students, Eloise Delaporte, we are currently looking into this principal parameterized approach for gravitational collapse, and so maybe I'll then at some point in the future be able to say more about whether loop quantum gravity does fall into this principal parameterized approach in that time dependent setting or not.
Okay. Now I see Ariel. Ariel, please try to ask your question once again, but switch on the sound. We cannot, we don't, no, okay.
Oh, thank you.
It's okay.
Hello.
Now it's okay.
Hi,
Hi, yeah, we can hear you now.
can you hear me?
Yes, yes.
Oh, yes, thank you. Yes, I have two questions. The first one is, I want to know if Heisenberg's uncertainty principle will not be a formidable obstacle to reach the scale of quantum gravity.
I don't believe that is the case. I mean, of course, there are sort of settings where one sort of modifies the uncertainty principle by quantum gravity effects and then investigates whether that might have some consequences in quantum mechanics. But I don't believe that happens here. To some extent, maybe this question translates into the question of, can you actually probe physics at the Planck scale directly, or do you necessarily produce black holes? And as I answered before, that isn't necessarily the case, and so there could really be meaning in probing physics beyond the Planck scale.
Oh, okay. Yes, but now, is there any field where we cannot observe the effect of quantum gravity by the optical spectrum?
Whether there's a field in which we can observe the effect of quantum gravity in the optical spectrum. I'm not sure I immediately have a good answer to that question. I would have to think about that a little bit more.
Oh, thank you. Thank you.
Okay. More questions, please. Some comments or questions? If there is no more questions or comments, let's thank Astrid once again for her excellent talk. Thank you very much. Thank you very much. Bye-bye.
Yes, thank you. Bye-bye.
Thanks a lot, Astrid.
Thank you, Astrid.
Bye.
Bye.
Would you send slides to me or to Luca at some point?
Yeah, I can do that.
Yeah, thanks.
Thank you very much, Astrid. Bye-bye.
Bye.